I got everybody quiet down so they can hear the introduction. So, I will introduce myself. I'm Raymond Hettinger, Python core developer and consultant and trainer and whatnot. And I'm here today to show you a list of tips, tricks, and idioms. What's the difference between a tip and a trick? A tip is something you should do. A trick is something that is cool that you can do but probably shouldn't do. I will show you some bad things as well as good, with the goal of actually expanding your knowledge about Python, which is always a good thing whether you use the trick or not. Fair enough? All right. For those of you who were here before, you know about this, the Twitter at Raymond. The way I get my feedback from the talks is I go after the talks and I look to see what you guys said. So the only way I'll know how to improve my material is if you tweet from the mountaintops. Also, it is helpful to me if you make everybody who's not here wish they were here. And then I ask that those of you who are interested in tips and tricks that you subscribe to my Twitter feed, because I aspire to at least once a day send you something, little thing about Python that can be read in under a minute for 30 seconds. And each day you'll learn one little tidbit of Python, including the new thing I learned this week. So who subscribes to my Twitter feed? Who doesn't? Okay, those of you who don't, what is a more readable way to improve situations where you're using Unicode, where you use /u in the Unicode string and the 4-digit hex code 034F? All right, those of you who follow the stream will know that you can use curly brackets and actually use the name of the Unicode character and say something like Arabic Indic digit 4. And that will be a more readable form, has exactly the same meaning for the Python interpreter with no loss of efficiency, amazingly enough. Who thinks it's fantastic? So, you want more of these tips? You know where to go get them. Right there. Alright, what's ahead? What I've done is put together a 3-hour presentation. And I like to do that for 1-hour presentations so that I can get a feel back from the audience. Anytime you're bored to tears, you think you already know something, just encourage me to go further, and I'll just say, well, I've got something else. So we will skip through it, skipping through parts that you don't like. So I'm going to show you a few of the unique language features and idioms. We're going to talk a little bit about comparisons and orderings, because it's amazing that people who use Python every day sometimes forget how all of that works. We'll talk about programming with iterators. And we'll take a look at some collections objects. We'll show you some optimizations and hacks. One of the tools that is underutilized in Python is PDB, the debugger. So I will do a very quick demo of that. And then I'll talk about your development tools and environment. It is possible here that everyone here is already using pip and virtual env and doesn't need that section. But if we don't get to that section, my recommendation is you learn about pip and virtual env, because the rest of your peers are using it, it's improving their lives. All right, let's go take a look at some of the unique language features, things that are unique to Python. One of them is slicing. So slicing is about half-open intervals. This is the math notation for it, not the Python notation. It says we're including the include to and excluding the 5. This is the way it looks in Python code. When you teach other people about Python, the moment you mention this fact, be sure you go to the second fact, which is part of the rationale for it. Otherwise, it just seems weird and arcane and like something we shouldn't have done, and will turn people away from Python if that's one of the first things they see. So you will show them that this invariant holds, so that 2 to 5 and then 5 to 8 is the same as 2 to 8. So you don't have to do what you do in other languages when you're carving out a string, where you turn that into a 6, and the language is full of a whole lot of, you're parsing a record layout with records that start at position A, B, C, and D. You can use A, B, C, and D as the start of your slice points. Go A to B, B to C, B to D, and none of this +1 and -1 rigmarole. So it's a very clean style of parsing of layout. Remind people that the abbreviation for a whole sequence is just using the colon itself. An amazing number of Python programmers who are very advanced scientifically, or in some other community, let's say genomics people or whatnot, they use Python infrequently enough to where they forget this sort of thing, which is a problem because they forget the idiom for copying a list is using C = S:. Like Dick has a copy method, Jack has a copy method, lots of things have a copy method, and a list doesn't, and people can't figure out how to copy a list. So that's our way of doing it. It's one of our idioms. Be sure you teach it early on. Likewise, we've got two ways of clearing a list. You can do del s colon, and we've got s colon equals bracket. Who has forgotten at least one thing that was on the screen? All right, good. Then that was a useful reminder. Let's go to a slightly more advanced topic. Negative slicing. So, -1 is the end. Probably most of you remember that. -2 colons, go back 2, and then forward to the end. So that grabs the last couple characters. This grabs the last two elements, one from the end. So this kind of thing is useful for chopping off the .html out of index.html. This is an empty slice because it starts and ends at the same place. And remember, it's a half-open interval. There will be nothing inside. So we're including that one, but excluding this one. Therefore, you get nothing. So if you want to go all the way back to -3. So here's the surprise. My bet is even the advanced users in here will learn something new. If I make this loop, and I do, I have several different values of I, 0, 1, and 2. I put them right here. I get an empty string, A and B. I never get, there is no value for the negative that returns the whole string. In other words, most people who do something where, if you see something like a -2 colon where they put a constant in, somebody has thought about the content of the string. If they put a variable here and it's negative, almost certainly they have a bug in their program. Every time someone uses a negative variable right here, very likely there is a bug where they never get the whole string. You learn something new. Okay, so that's one of the arcane pieces of negative slicing, and that's why I brought you to this class today to take you from advanced knowledge to knowing the corners of Python. All right, let's go to one of the other basics, tuple sequence, packing and unpacking. So you do this all the time, so this part's probably not new to you. You can go by a tuple and pack it over here. One of the things I'm going to point out here that most of you would miss on a quick quiz, if you were describing without the interpreter in front of you how tuples are formed, most people would say something about parentheses. Parentheses does not a tuple make. It's the commas that make tuples. Parentheses are only necessary for one tuple. For some reason, but I know the reason, because tuples display with parentheses, we tend to think of parentheses make a tuple. What does a tuple make? Commas. These are fantastic. Okay, so here's the way you unpack. By the way, easy enough. This tuple has to be of length 3, otherwise the unpacking will fail. Thou shalt count not to the number 3. You know the rest. 4 is right. All right, what else is interesting about this? What's interesting about this, I think, is that what actually happens here is on the right-hand side, these pieces are executed one at a time. This expression, then this expression, then this expression. We say that what happens first is on the right side of the equal sign, the expressions are evaluated left to right, one at a time. Likewise, when we unpack, the tuple comes in and unpacks one piece at a time. The assignment to A is done, then B, then C. Who cares? I don't We care because sometimes it matters, because something here can affect the unpacking here. Don't look to the bottom of the screen where it's should be ahead. All right, so tuple unpacking and unpacking, the two can be combined together, which is fantastic because the operation of this does not assign A to 1, 2 to B, 3 to C in that order. In fact, what it does is evaluates this expression, this one, then this one, takes the result of that, forms it into a 3 tuple, then unpacks it into A, then into B, then into C. Way different than if A went to 1, B went to 2, 3. So one way you can use this is for swapping values. So this is the Python way to swap. It saves you from the 3-way dance that we just talked about in the previous talk, so you don't have to use an intermediate t value. So the tuple is formed here, t, and then the tuple is unpacked. That's the way this works. Otherwise, if B was directly assigned to A, that will have mutated A before the second assignment happened and the swap wouldn't have occurred. So the way swaps happen is this ordering. Expressions are evaluated left to right on the right-hand side of the equal sign, then a tuple is formed, then that tuple is unpacked left to right. So, how can you mess this up? I want to update an index, and I want to update an array at that index. If I take 1, 2 here, what will happen is 1 is evaluated, then 2. We form the 2 tuple. So we've got a 2 tuple, 1, 2. We unpack the first one, the 1, and assign it to I. Then we take the 2 and assign it to A at I. But I has changed. So the assignment here will update, no matter what I was beforehand, it will update I with at position 1. If I switch the order of these 2 arguments, if I put a 2, 1 right here and AI, comma I, it would behave differently. We learned something new. Okay, some details of how Python works inside, and it matters in cases like this. All right, the basics of Python. Python way. Not to program like we learned in C and BASIC and whatnot, and use indices to look up into our arrays. Pythonic way is to use things like append and pop. And then to loop over lists with for, x, and s. Note there are no indices in any of those 3 expressions. Those are ways to build up a list, shrink a list, and loop over it. And so if you program that way, Python programs have this nice property of we never have off by 1 errors, or at least not in this kind of code. So we try to avoid code that looks like this. And why is this important? You guys have been to Python. You're learning a lot about Python here. You're part of the Python community now. You are now leaders. You're going back to your company. You're going to be teaching other people Python and showing people the Python way. When you see this code, which they will do if they learn it in any other language, because this is the idiom in many other languages, it is the one true right way, you're going to help them step forward and program Pythonically. Do this instead of that. So I hope you didn't learn anything new. What I do hope is that you have a message that you're going to carry back. What is the Python way? Python the way Guido intended it and the way he intended it. Python idioms. Iteration idioms. There's the for item ranged in, for element and sequence. And then I consider these others to be the remainder of the core idioms of how we loop. So the way to go over something backwards is to use reversed. Now, what if you're doing splicing? Well, slice has an option to do, put a -1 option on it to loop backwards. Is that the Raymond way? No. The Raymond way is to set up your slice to go forwards. Pull out every second element, out the first 10 characters or whatnot, and then wrap reversed around it so that it goes backwards. Why? The reason is because Python has half-open intervals, which includes the first part and excludes the second part. When we reverse it, it changes the notion of which side of that interval is open. And so it blows our mind, which has become accustomed to, because we've written range and whatnot, we get used to how to interpret those. And if you use negative slicing, it is incredibly difficult to look at these start and stop indices and to know whether they're correct. Even advanced Python programmers have to do a double take and mentally work out +1s and the -1 is this piece included and excluded. And it's very common for even advanced Python programmers to make the string A, B, C, D, E and then run to 5:3:-1 just to see which characters get pulled out. We relearn it by experiment. The better way is, you know how to write slices forward. Write them forward, wrap it in reverse. So we learned a new technique, the Raymond way. All right, fantastic. All right, and then enumerate. It is the correct way to get the indices. It's also faster than using I = 0 or looking around. Iterate also now takes a start argument so you can learn to count the way you did in school. Or I and page in enumerate pages. The book starts with page 1, page 0, the way it goes to the world count. And when zip was first proposed, the title of the path was called Lockstep Iteration. And it's the way to lock this concept into your mind of what is zip for. Zip is really all about being able to do 4x and y and looping over 2 sequences. And these are the Python core idioms. So when you're showing people Python and they're just getting started, teach them to program this way. It beats the heck out of doing it with indices. So let's see if we can get to one of the basics that you might not all know. Who remembered that Python had else clauses that could be used with for and while? Right. So the reason they were introduced, you go back and look at the seminal papers on structured programming constructs. There was one by Donald Knuth called Structured Programming Without GoTo, or something to that effect, where he came up with a list of use cases of things where it seemed like you needed GoTo. And said, if I didn't have GoTo, what kind of structured construct would work? And one of his cases was, if you're doing a find type operation, you're searching over a sequence, you're looking for a target, and then you have a break when something's found, but then you need some action when the case is not found. The traditional way to do this, if you didn't have the else clause, and you didn't have GoTo, the old way is to make flags. So you start with a flag before the loop, not found, then if found, set found equal true, then after the loop, have an if not found handle that case. So this else clause triggers whenever the iteration gets all the way to the end, it doesn't encounter a break statement. So this is basically saying, in the case where the target is not found, execute this code, whatever that code is. Keep in mind, this simple example, we could have just used a return, and it would have worked just fine. You kind of get the gist. The else clause is for the case where the looping runs all the way to the completion. When does a loop run to completion? It's actually the normal case in Python. When does a loop not run to completion? When we have a break. So else clauses only make sense in for loops that have a break inside. Because basically what the else clause says is, I got to the end without encountering the break. Okay, so what's interesting is else clauses are often presented in an abstract way that is divorced from their use cases, why you would use it, and often presented without mentioning the break statement, which is the only time you would want to use it. So if you communicate this feature to other people, always mention that it's only useful when a break is present, and always present it with a motivating use case, which is the searching use case, which goes back to Donald Knuth's paper as a core recurring use case that occurs over and over and over again. So who learned something new with either the use case, the way to present it, or the association between for else and break? All right, fantastic. And that was a worthwhile slide, and I will keep it. Let's go into the comparisons.
It might be nice just for documenting too, right? Even if you don't need it, even if you just do a return, it might be nice to.
So the suggestion would be using code to document what is going on. And
at a glance, you can see what's happening.
so at a glance, you can see what's happening. And if by that you meant using an else clause to say, as a way I got to the end of the loop, I would say no. But if by that you meant do what I did and add comments here, hey, this is the case where X is found and this was not, I would agree. So the reason not to use an else in the absence of a break is hopefully we have deeply associated in your mind today, else's and breaks are very tightly bound together. So it would be like in BASIC, like having a for without an next, or a if without an end if, it would, or a while without a when. It would tend to break somebody's concept of how the thing works. So I would never use the else clause in the absence of a break, because it causes my mind to immediately look for the break, and then I presume that the programmer has made some error in logic and in their thinking style. Fair enough? No, it's always reachable, because the loop will run to completion, and what the else clause means is the loop running to completion. Experiment and it'll become self-evident. Okay, comparisons. By default, all types are comparable in Python 2. We have specifically made some types non-comparable, like complex numbers. Interestingly, in Python 2 and not Python 3, none has a special property of being less than everything else. So it's fantastic. We sort of list all of the nones will come to the beginning. Give me that. It's an arcane feature of none. So it saves you from writing a class called negative infinity, so that you can create objects that always sort to the top of a list. And I see lots of negative infinity ones, but positive infinity, there's use for that. Positive infinity is something that compared larger than everything else. You could use it as a sentinel or some type of loop termination marker. Okay. So we have rich comparisons now, which means one at a time you can override comparisons like less than operator with under LT. Notice I didn't say under LT, under. Reasons? shortcut. Or I could say double under R&D, new term of art. Wesley's cringing. Hold your ears. Dunder. Okay, so Dunder LT. It's kind of weird. Pretty Californianist. All right. So the problem with that is there's no guarantee that the ordering is consistent. For instance, I overrode less than for sets. So when I implemented sets, I overrode this, and this now means an is subset test. So it's possible to have one set that is not a subset of either two other sets, and this returns false. And then I flip the sign on and do a superset test, it returns false. And then I try equality and it returns false. It should blow your mind with the notion when it comes to the notion of ordering, because something should at least be less than, equal to, or greater than, right? No, because this is a subset super test. Meaning that if you take sets and feed them into sort attempts to order them, the outcome is arbitrary, not necessarily predictable or repeatable. You learn something new. So ordering is no longer guaranteed amongst all objects. So functions that use the ordering, things like sorted, for producing sorted lists, min and max, got the key cube module, in smallest and in largest, give me. Notice how amazingly efficient in smallest is. All right, so min, I want to take the min of 1 million inputs. How many comparisons do I have to do? 1 million minus 1. If I want to take the 1 million elements in and I want the 100 smallest elements, how many comparisons do I have to do? 5 million? 10 million? Nope. Million plus several thousand. It's shockingly efficient. It's almost as efficient as min, even for large numbers. It's fun to play around with that algorithm and convince yourself that that is true. If you do, you'll learn a little bit about algorithmics. Bisect and insort also use ordering functions. Which ordering functions do they use? They all use the under LT. What's good about that is they're consistent. What's bad about it is you might come to rely on it and you'll create a class that only defines under LT. But then would you be programming the Raymond way? No. And it's now the Raymond way has now become the Python way. But in FA, thou shalt not only define under LT. When you provide your core, if you intend for something to be orderable, you should also define GT, GE, etc. All 6 of the ordering comparisons. Otherwise, people can't do basic math with your objects. They say, well, if A is less than B, but then they can't reorder it to B greater than A. It doesn't necessarily produce the opposite result. And because of the way in which comparisons are implemented, they might not know. It'll come back and return false. Hey, it looks like it's working, but in fact it doesn't. So my recommendation to you is even though all of these are guaranteed to use under LT, how many methods are you going to define? 6. Thank you very much. Key functions. This was a Raymond. I put this into Python. It encapsulates the old notion we used to. There was old knowledge that you needed to acquire, which was decorate, sort, undecorate. Also known by the name of the Schwartzian transform. That is old knowledge. Do it now for you with key functions. But we have new knowledge. New knowledge is sort has some special properties. We'll look at that. Actually, make sure I don't go off the slide before we talk about sort stability. Here, I want to talk about just the ways to use key. So I can pass in an unbound method like string.lower. That will do a case-insensitive sort. Pretty cool. There are people who think that unbound methods are simple. But they are the Python way. You can't do this in a statically compiled language, so it feels weird to people who came from that language. It is the norm of Python to be able to use unbound methods and bound methods freely as if they were any other type of call. It's what we do. So it used to. Likewise, it used to lambdas. There are a lot of people who hate lambda. They pleaded with Guido, get rid of lambda. And he listened. He almost gave in several times and finally said, lambda stays. So, equal lambda, pull out the second element of some sequence. Simple enough. So this sorts on the second field as a primary key for a sort. Another way to say that is to go into the operator module and use item getter, which says get the second item. Item getter can take multiple arguments. So I can say pull out the second field, the fourth, and the sixth, and form a tuple and do a comparison based on that tuple. These tools in Operator are actually shockingly powerful. They can handle nested lookups and all types of stuff, which you would know if you followed a certain Twitter stream that I won't name your name. Okay. This is another style. Instead of using position, you can do name lookup. So take a record and pull out the last name and first name. Other way to write that is from the operator module, say, do an attribute getter at last and first. These two are the same. These two are the same. Some people prefer this style. Some people prefer the lambda style. If you hate lambdas, use the attribute getters and attribute getters. Which raises the question, how do I sort by one field ascending and the other descending? Oh, wait, before we go there, when I mentioned this sort by this ascending and sort by that descending, what does that remind you of? SQL. The new way to think about sorts is in the SQL way. Order by last name, order by first name. Order by last name, or order by department, and then order by last name descending. How do we do this in Python? The new skill in Python is to make two passes at the sort. So the sort is stable so that when you first sort by department, okay, everybody's grouped together by department. Then when you sort by age, reverse, everyone who has the same age will retain their department ordering. So now you have a sort by age descending as primary key and sort by department as secondary. We learned a new skill. Fantastic. Oh my God, Wesley raised his hand. This morning was my time to learn all kinds of good things from Wesley. I was hoping to do one to return a favor, and I just got my hand. If you haven't seen Wesley teach, you really are missing out. Okay. I believe that iterators are the most important concept in the language, and they keep the language simple and clean. So, I mentioned this in the advanced Python classes, some of you have already seen. What is iterable? Strings is lists, tuples, sets, dictionaries, text, files, URLs, generators, anything with a get item, or anything with an object with under iter. The part that might be new to some of you here is I've mentioned anything with under get item. Amazingly, if you define get item, iter will attempt to take the get item and call get item 0, get item 1, get item 2, and it will make it iterable for you. One way to discover this is if you practice test-driven development. You go ahead and write your tests first. You've already defined a get item. You say, I need to define an iter method. So I list my object to loop over it. I write the test. In the test-driven development style is to write the test before you've written the iter method. You run the test, and the test succeeds. I didn't write iter yet. We learned something new with that. That's one of the little hidden features inside Python. And it was the reason for that is the get item protocol predates the iterator protocol, and so we have lots of code that uses it. What uses iterators? Mainly for loops, but also lots of things consume them. Sets, sorted, int, max, list comprehensions, generator comprehensions, dictionaries, etc. The important thing is it is the glue that puts everything together. So here's the Zen codes of Python. Things to just meditate on. I have the sound of one hand clapping. These two pieces of Python. I take the string abracadabra, I feed it into set, and I feed it into sorted. So feeding abracadabra into set uniqueifies it. It eliminates all the duplicate letters. Then set goes into sorted, and it arranges those in sorted order. And that's not a particularly useful application. Why is this important? Because it shows I took something that was iterable, fed it into something that consumed iterables. It was iterable itself, because sets are iterable, fed it into sorted, which is iterable, and it returned another iterable list. That was the glue that held these pieces together. When I worked on sorted, I was not thinking about sets. When I implemented sets, I was not thinking about strings. I took tools that were not originally designed to work together, and yet they can be stitched together easily. My recommendation is when you build your classes, you make them so they can consume arbitrary intervals, and they emit arbitrary intervals. And if you do so, you'll find that Python has a huge pile of tools to let you cobble things together. So let's take this piece of code and do something cool. Because what did this code do? It took some input, it uniqueified it, and it sorted it. All right, to knock out that string, because that's kind of a boring string. Instead, I'll replace this with URL div open. Ooh, that reaches out to a URL, pulls down a data set, drops it in a set, uniqueifies it, and emits it in sorted fashion so I can loop over it. I can drop any interval in here. Open a local file, all kinds of things can go here. So this is actually a fairly powerful construct. So you've got the idea of one little data item coming out, one into another, going into another, which reminds us of something. Pieces that were a stream of things connected together with some type of glue that connects them all together. What does that remind us of? Unix pipes and filters. And when you get reminded of that, you'll embark on one of people's favorite projects, which is to re-implement pipes and filters, and they'll try to override the Python OR operator and try and make something that actually looks like pipe and filters. It's a fun exercise, but it never ends up in something that's particularly useful code. The important thing is there's some analogy here between pipes and filters and what we do with iterators. That's why they're so powerful. So you've got this notion of one thing flowing into another tool, into another tool. What if I want to pass two? That's why we have the second Zoom cone. I want to enumerate ABC and flow it into dict. Dict accepts an interval, but that interval needs to be an interval of pairs, key value pairs. So this actually produces something that looks very much like a sequence. And so if I look up in this dictionary and go D brackets 0, it'll hand me the first item, D brackets 1 the second item. In other words, I can create dictionaries that look exactly like sequences, but have the full dict API. It's kind of fantastic. Easily done. And the important thing is, we're not just taking single data elements out. Enumerate is returning pairs, an index and a value, and dictionaries consume it. This glue works just as well for things that consume intervals and pairs as intervals and singletons. Learn something new. Meditate on these two, and you've got it. All right. Iterators are cool. What's the easiest way to make them? Okay, so in the beginning, we didn't have generators. We were reasonably happy. We wrote a class that had an iter, it had a next method, it had an instantiator, and stored its state. It was kind of a pain, and generators came along and just made it so simple. Well, could there be an even easier way? Little known tool, because this is all tips and tricks. So the iter function has a form where it takes two arguments. And the first argument is any callable, let's say f.readline. And how do you know when f.readline is done? It returns an empty string. So the second argument is some sentinel value. Like I will loop over numbers until I get to the number -1. I will loop over lines of a file until I hit an empty line. We can combine this with functools partial, so I can make something that makes a chunk reader that says do an fread 20 bytes at a time and loop over those blocks until I get some block that is an empty string, which is how f.read signals that it's done. The old way of writing that is we do a while true block, we do the fread 20, then we do the if the block is equal to a blank, and then do a breakout. I've seen this code 1,000 times. This isn't gorgeous. I get to use a for loop. For loops are pretty explicit about what we're doing. We are looping over the file in binary chunks. We learned something new. Fantastic. All right. So I talked about the old days. All we had was an interval protocol, no generators. But we can go even further back. When my father programmed, his grandfather programmed. In the old days, we had super. We were happy. Super had a very simple, specific meaning. It was fast. We used it in small talk, and all types of languages have super. So Python got one too, but it's different. It's not your father's super. What does everybody else's super do? Everybody else's super reaches into a parent class, somewhere up the chain of parents. And so we know when we're writing a class what that chain of parents is. If I have made a subclass of dict and I call super, I'm referring to dict, always. But that's not what Python super does. It has nothing to do with the class, or very little to do with the class you're currently in. It has everything to do with self. Self might be an instance of something else. How can it be not a member of me? Well, it could be a subclass of you. written a class you call super, but self represents an object in some subclass of your class. Possibly many layers down. Possibly with multiple inheritance. Possibly with a method resolution order, a chain of parents, that you could not have imagined when you wrote your class. And what super will do was call the next parent in that child's chain of parents. So, to use the analogies of fathers and sons, I get this notion that I have a super. My super says, call one of my parents, my dad or my grandfather. But it does something else. I end up having a daughter. She ends up having a son, who ends up having a daughter. And they marry. And other families come in. Perhaps one of my grandchildren will marry one of your grandchildren. And when they do, they may call the method using super. Meaning that when it gets to me and I dispatch my super call, instead of dispatching it to my dad, I might actually hand it to one of her ancestors, somebody who I haven't even met yet, one of you in the audience. So my super call might not call my dad, it might call one of you, simply because my great-granddaughter married your great-grandson. Are you with me? No, you kidding? All right, what can we do with this? So we got ourselves a counter. You remember the counter? If we were in the last session, counter inherits from dict. And one of the first lines in counter does a dispatch to its parent by saying super. But super doesn't mean go to my parent. Super means whatever I'm an instance of, go to its next in the method resolution order. So the semantics of what it means to use super. It's anytime our counter uses super, we don't think of it as one of our parent classes. What the counter is saying is, I am relying on some other class to do my mapping work. If I've not specifically implemented a get item or a pop keys, I'm going to hand that off to some class that has a mapping-like interface. Okay? So that's what the counter is thinking. And it says I'm going to provide a default for that. The service that I am currently, by default, wired to is dict. So if you ask me dict pop, and I haven't defined pop, it is it's dict pops that's going to do the work. If I have defined a get item and I use super, when I make the super call, I'm not saying call my parent, I'm calling whoever provides the mapping service. So do you guys have a new mental model for super now? It's not about calling parents, it's whoever provides a certain service. It is a form of delegation. We are saying that counter delegates its mapping work to another class. And by default, that class is dict, the one we inherited from. How can that be changed? How can we reassign it? Here's how we do it. Let's make a subclass, ordered counter. My son is going to marry your granddaughter, ordered dict. The code on the right is pass. It takes no code to make this work, which is fantastic. All we had to do was have the marriage. Now, an instance of ordered counter now has a new method resolution order that says, first I will check counter for a method, and then I will check ordered dict. And only after it will I check things like dict itself. So essentially, ordered dict has now been inserted between counter and dict itself. So the semantics in counter is, I need to save something in a dictionary. I will delegate that work by calling super. Super is by default dict, but it could be somebody else. And a new provider of that service now is ordered dict. So it provides a very elegant way to rewire that service, a form of reprogrammable delegation, which is fantastic. Because if you design your classes with this in mind, and I'll teach you how to do that tomorrow, your classes will be composable in ways that you might not even imagine. It's a fantastic thing to do in the program. It tells you that you've been successful. Hayhoe, Kernighan, and Ritchie wrote Hawk. They were just trying to marry together set and add some programmability features to things that would be familiar to C programmers. And the idea was you'd write a little programmable set script that was 3 or 4 lines long. And they're afterwards of the book, he said they fell over with shock the first time they saw an awk program more than 10 lines long. So I aspired to meet them someday and show them the flight simulator that I wrote it on. The point is, they wrote the tool well enough to where it was usable in ways that they couldn't even imagine. I will show you tomorrow how to design your classes so that people who come after you, the subclasses, will use them in ways you can't even imagine. Because I did not write counter with the intention of making it work with order dict, and I did not design order dict with the intention of making it work with counter. But because I followed some good design principles, they marry up with this. I could actually put this pass in this line, and it would be a Python one-liner to create an ordered counter. Who thinks that's fantastic? So the takeaway here is this is not your father's super. In fact, we would have been far better off to have not called it super and given it any other name, because super creates a misleading impression that super has something to do with parents. And why do people have this misleading impression? Because every other language in the entire universe, except for Dylan, their super has a different meaning than ours. So we chose a bad name for ours. Fair enough. Let's go to something fantastic. If you'd like to know the details of how to do it, you can see my blog post, Super Considered Super. How am I doing for time? 5 minutes? All right. Collections module, I'll give you just a quick overview. There's collections deck. Deck works very much like a list, but lists don't behave very well when you do a pop 0 or insert 0 because it has to move all of the entries over by one to make a space. So deck has been optimized so that you can append and pop from either the left side or the right side with full efficiency. So it is used for whenever you need a queue. I'm adding a list of tasks.
I'm not talking.
Who is talking? Okay, if that continues, I'll just take off the mic and I'll shut off the speaker. Let's not take this off, I'll just talk loud. Will you shut down our speaker? If you can get it turned off, I'll just talk loud.
So if I were to try the latest version,
I know that voice. We know the culprit. Okay, so what deck does is it appends and pops very efficiently from both the left and the right side. So one of the simplest ways to optimize your code and make it scalable is to go back to your office and do a grep. Grep-R for pop 0. Anytime you see pop 0 or insert 0, it is a very strong indication that you're using the wrong data structure, but you're using a list when you should use a deck. If you replace that, you'll find that you get scalability. You will replace a win operation with an O1 operation. Even if you don't use deck, you'll be getting a benefit from it because I've used deck internally in a number of tools like collections queue. So queue objects are based on deck, so you get the O1 efficiency there instead of the way it used to be implemented using list. Name tuples, we talked about them earlier. Essentially, they provide attribute access to tuples so that you end up with better documented, more beautiful, clean code. You were in the previous session, you learned that there's some amazing things that can be done with this that can be pushed quite far. Default dict is something is a dictionary whose missing method calls a factory function. So default dict list says if we are accessing a dictionary element and it's missing, it will create a new empty list as the default value there. And so it lets you write code like this, dk.append, knowing that dk will always return a list and that you can append directly without first checking to see if it is empty. Counter is simply a dictionary that knows how to count. So it's great to very clean code because 0 plus equal 2 without having to check to see if they already exist. Then finally, there's order dict. Order dict takes very little time to learn to use. You basically put in like 2 paragraphs of documentation that says an order dict remembers the order of the keys were first inserted. So if I insert the keys A, B, C, and A, the order in the dictionary will be A, B, C because A was first inserted before B. It's fantastic for doing things like you read a configuration file, a JSON file, an XML file, make some modification to it and write it back out. When you write it back out, it'll be written in the same order the person wrote it in the first place and it'll be easy to validate that you're changed. If you use a regular dictionary, the order will tend to scramble and it will become increasingly more difficult to validate the change. And so the humans whose eyes look at this code will appreciate you greatly for using order dict. And it has weaker performance than dictionaries. It has the same big O notation performance, so it deletes as fast, inserts as fast, but it is proportionally slower by a factor of 5 to 8, depending on your machine. So it's not the fastest in the world, but it is scalable, and it's very clean. I recommend it highly. All right, do we have any minutes left, or is it time to go to video? Okay. 1 minute for questions? Or?
5 minutes for questions.
Okay. Yeah, I'll show you something funky here. Because I promised some tricks, although this is labeled as a tip. It's kind of a trick. Ways to make sparse 2D arrays using dictionaries. So make a default dict. Then it takes the dict as a factory function, and so it supplies a missing value. People are laughing at us, so there's something funny on that scene. So the idea is I can write the Canada, Quebec, a dictionary pointing to a dictionary, and I don't have to worry about whether Canada has already been instantiated in the outermost dictionary. If it was missing, this will create one for it. It is a fun exercise of recursion with a very interesting end case to make this, to create a recipe for this that is multi-dimensional, so that you can do a 5-dimensional array, so that you can make sparse matrices. So the old way of doing that is you'd have to do a dict, create the entry for Canada, and then you go inside Canada. You learn something new. Okay, no PDB for you, no optimizations for you. Oh, a couple tricks. I didn't tell you this. If you take a dict, wrap it in a dict constructor, it is guaranteed to make a copy. So it makes a new dict just like the old one. Now if I take the old one and I do an update on it, it doesn't recognize that it's updating against itself. So it makes space inside for a second full dictionary just as big as it was, not knowing that the same keys and values are going to come in. So D will be unchanged after this operation semantically. But it will have doubled in size internally because it's based on a hash table. You will have sparsified it. So you can take your built-ins, for example, run this on built-ins, and it will sparsify them and make all your built-in requests faster. So all the things that had collisions, where you looked at power, int, or value error, and there was a collision being sparsified, it's less likely you can have a collision. How would I use something like this? I would not put this in the main body of my code. I would write a def on the outside, sparsify. I would add a comment about how it works, and then I'd also note that in other implementations of Python, it's not guaranteed to work, but if it doesn't work, at least it is semantically guaranteed to not change your dictionary, so it never hurts to use it. So I'd wrap it in sparsify. So if you use a grotesque hack, the way we do that is we isolate it in one piece of code, a nice function definition around it that says what it does. Def sparsify a dictionary, runs this on it, and it works on all current versions of CPython. It doesn't hurt any non-CPython version, so it's never bad. But it's a kind of a grotesque hack. But we isolate it and say, well, it's some attempt to improve and inform. We've learned something new. Okay, I didn't tell you this. I also didn't tell you that the way Python switches threads internally is it has a counter, and it counts how many steps that it's performed. Let's say a check interval does 100 steps, and then it checks to see if another thread is waiting and switches over. So a poor man's luck would be to take the check interval, save it, set in a new one, a sysmax int, which a bazillion computations have gone by, and then you can task switch. Now you are guaranteed that no task switches will occur while you take something like do a max of a task list and remove a value. You do want these two operations to occur atomically, because if you find the max and then you try to remove separately, if another thread had come along, it might have taken off the highest priority task, and so there'd be a disconnect between these. Then you turn the check interval back on, and all the other threads can come. Unlike using locks, this is never guaranteed to never deadlock. Okay, I didn't teach you this, and it doesn't work now in Python 3 now that Antoine has changed it to use actual wall clock times of steps, and it is likely to change again because it didn't actually improve improve the multi-threaded informants like it was supposed to. So my buddy David Beasley is working on a fix now so that we'll have a different version of Python 3.3, and then we'll have a different one in Py 3.4, but by then we'll all be using PyPy, and it will not matter. Okay, thank you very much for coming. I hope you love it. Everyone who wasn't here, make them wish they were here by sending some feedback to Raymond.8. Thank you, guys. Oh, so oh, sure. I'll take that.
Was that talk given in Python 2 or Python 3? Because you talked about how all objects are comparable or not. Sort of glossed over that distinction.
Yes, the comparison situation is much more complicated in Python 3. I will leave it at that because it's its own subject that I have not fully worked out. By default, everything has defined under your LT, but it returns not implemented. So it is very difficult now to tell in Python 3 whether objects are comparable without calling them. When you call them, you get a false. You don't know whether that means something. So it's a long answer to this short question. Mr. Chisholm, we got it here for Chris.
A very quick one. It was about the counter class where you said you can put any object into
Any hash form.
any hash code.
Yeah, because it's just a dictionary.
Sorry, time is over. Should maybe thank Raymond again.